All right, go take your textbooks out and open to page 31. Have your homework out. Let's take a look at questions 6 through 9, 12, 14, 16, and in a little bit we'll take a look at problems 2, 4, and 6. Question number 6 asks, or says, list and identify the location, or list the identity, and location of the 3 primary particles that compose an atom. Michael, what'd you have?
The 3 particles composing an atom are the proton located in the nucleus, the neutron located in the nucleus, and the electron which floats around the nucleus.
There we go. And number 7, what is the charge of a neutron, of an electron, and of a proton? Audrey?
Charge of a neutron is neutral. The charge of an electron is negative. Charge of a proton is positive.
Good. Number 8, distinguish between atomic number and mass number. Kendall?
Atomic number is the number of protons in an element. Mass number is the sum of the number of protons in neutrons.
Very good. Number 9, what's the difference between isotopes and ions? Michael?
Isotopes are atoms with the same atomic number but different mass number. Ions are electrically charged atoms.
Okay, good. Another way, anyone have a different explanation? All right, here would be my differentiation, because why would a person get the 2 terms confused? Well, an ion has either gained or lost electrons, hence the charge that Michael mentioned. An isotope has either gained or lost neutrons, usually gained, hence the change in the mass number. So they're both gaining, losing things, right? It's just one is neutrons, which changes mass, one is electrons, which changes charge. So that's why it had them differentiate between the 2, but the 2 definitions were perfect. Let's go on to number 12. Name 2 kinds of pure substances, Kendall.
Homogeneous and heterogeneous.
Those are actually 2 different types of mixtures. Audrey?
And the same thing.
Had the same thing?
Radon and argon.
Okay, wasn't looking for 2 examples of pure substances. So what they were looking for is elements and compounds are 2 types of pure substances. Elements and compounds are 2 types of pure substances. Number 13, we did in the previous lesson. Number 14, what equation relates mass and energy? That question sounds familiar here. Back to Kendall.
The equation that relates to mass and energy is E equals mc².
Excellent. Number 16, this also sounds familiar. What particle of energy is found in a beam of light? Audrey?
Photons are particles of energy found in light.
Excellent, good. Any questions on the homework? We'll get to the math in just a minute. Before we do, let's review some terms from yesterday. We said anything that has mass and takes up space class is called matter. Very good. And we said that all matter has this unique property, that it tends to retain its present state of motion. That is, matter in motion tends to remain in motion in a straight line at a constant speed unless acted upon by an outside force. Matter at rest tends to remain at rest unless acted upon by an outside force. What's that property called? Audrey?
Inertia.
Inertia, good. We had 2 definitions of mass yesterday, Michael. Do you remember either of those 2 definitions? For what is mass?
Anything that has matter and takes up space.
Anything that is matter and takes it. Kendall, can you help him?
The amount of matter in an object.
The amount of matter contained within an object, but the better definition, anyone remember? The amount of inertia an object possesses. The amount of inertia an object possesses. That's mass, how much stuff there is, right? If we sent Michael up to the moon, well, actually, he would have more stuff because he'd be wearing the big old spacesuit and whatever. But Michael himself, independent of spacesuit, would still have the same amount of stuff, right? He'd still be Michael, he'd still look like that, okay? But he wouldn't weigh as much. What's the difference then between mass and weight, Audrey? Michael? Mass and weight.
Mass and weight. I know what weight is. It's the force of gravity.
Good. So weight is how much gravity pulls, for instance, on this water bottle, whereas mass is simply how much water you got. This goes to the moon. There's still the same amount of water, so the mass doesn't change. It'll just weigh differently because gravity pulls differently. So weight is simply the pull of gravity. If we were to look at the amount of mass divided by volume, for instance, if you have a little ice cube, right, versus the same size cube of, say, iron. I don't know why you have a random iron cube, but if you did, they take about the same space, same volume. One has a lot more stuff packed into it. What do we call the ratio of mass to volume? Back to Audrey.
It's
Density, very good. Do you remember what Greek letter we used to represent density, Kendall?
Rho.
Rho. It looks like a lowercase p, but it's the rho. And do you remember the equation for rho, Michael?
Something over volume.
It is something over volume. It's mass over volume. So rho equals m over v. Good. Where we said mass class will measure in what units? Grams, or later on we'll use, but for now we'll use grams. And volume will be measured, class, in cubic centimeters, or later on cubic meters. So the unit for density will be grams per cubic centimeter, right? It'll simply be the ratio of those units. And we practiced with those equations in our homework last night. Another thing that we've used in the homework last night was this idea of specific gravity. Anyone remember the other term for specific gravity?
Relative density.
Relative density. Density of something compared to some standard, right? So we simply take a density of, say, Michael, and we compare him to the standard, which would be water. And if he's more dense than water, we say he's dense. If he's less dense than water, we say he's not dense. And the only way to know would be to throw him in a pool and see what happens. Because if he's more dense than water, what happens to Michael? He sinks. If he's less dense than water, he floats. Now, a lot of our body is water, right? And bone and muscle and different organ tissues, right? So, what would make Michael more dense? What would he have to do to become more dense? Get buff, work out, right? And that way, when he goes in the water, he drowns. But if Michael just became a corpulent fellow and did consume snacks constantly, he would be flabby, which is less dense than water, so he would float. So, being flabby can save your life. It also causes heart attacks. All right, anyway. We're actually going to look at a number of instances this year where, like, technically, you have a better chance of survival if you're fat. And, and that's not advocating for this. It's not a health class. Okay? We're just looking from a physics perspective, but from a physics perspective. Anyway, I digress. So specific gravity. So this takes a density and compares it to the standard. What is the standard for a solid or a liquid? I just mentioned it a moment ago, class. Water. And what is the density of pure water, class? 1 gram per cubic centimeter, right? And so that works out really well for our purposes. For a gas, what's the standard? Hydrogen. And anyone happen to remember that standard? There's several zeros. There's 4 zeros, actually. And an 899, yeah, grams per cubic centimeter, which basically makes all the other gases seem really dense because they're all more dense than hydrogen. Right, so let's take a look at the homework problems then. We had problem number 2. It says a block of wood measures 15 centimeters by 16 centimeters by 25 centimeters and has a mass of 960 grams. What is its density and what is its specific gravity? What was the first thing we had to do, Kendall?
You multiply those and add those numbers. Multiply those numbers.
Which one?
Multiply.
Multiply them, right? Because to find volume, we multiply length times width times height. And what was the volume of this block of wood? Didn't write it down. All right. Anyone have it written down?
6,000.
6,000 cubic centimeters. And the other number they gave us was, Kendall, the mass of the block of wood was
960.
grams.
Yes.
Was that 960 point grams or just 960 grams?
Just 900.
Okay, so 2 sig figs is what we're looking at. By the way, this here would look like it'd be 1 sig fig, correct? But this was a number we obtained from these others. So we're going to still roll with the 2 sig figs from the problem. Now we want to know the density. Density is the ratio class of an object's mass to its volume. So we simply take the 960, we divide by the 6,000, and I think this worked out semi-evenly here, Kendall.
0.16.
0.16, that's already the 2 sig figs we knew we needed. So we'll say 0.16.
Grams per cubic centimeter.
That's the first answer. How many had that first answer for the density? All right, the second part of the problem says, what's the specific gravity? Well, what state of matter is wood? Solid. So we have to compare it to water. So we're going to take this density and divide by the density of our standard. And since water has a density of 1 gram per cubic centimeter, what's my answer going to be for this specific gravity? Class? 0.16. 0.16 what? Nothing. No units. So there's my first answer, and there's my second answer. How many of both answers correct? Questions on the second part? All right, take a look at number 4. It says an aluminum sheet has a mass of 212 grams. What is its volume? All right, so we know the mass, that's given to me, of 212 grams. It wants to know the volume of this sheet of aluminum. I feel like they only gave us one number. I feel like we're missing something. What else would we need to know here, Michael, in order to find volume? The density. And Michael's already flipped back in the book to find the density of aluminum.
2.70.
2.70 grams per cubic centimeter. All right, so if I want to take this equation but solve it for the volume, Audrey, what would I need to do?
Multiply.
Trying to solve for the V right here, and it's in a denominator. We said if it's in a denominator, how do I get it out? Kendall, help? Alternate it out. Just switch places with these two. So my equation is going to modify. I'm going to say that V is equal to, back to Audrey.
Rho over 212.
If I just flip this, then V now is equal to,
212.
don't plug in numbers yet. Just, what's this formula rearranged for V? I'm not asking for an answer yet. Flip them, what do we get?
Rho over M.
No. Flip these two. Alternate these two guys. M over rho, right? The V was in the bottom, so the rho goes in the bottom. The rho goes in the top, the V goes in the top. So we just get M over rho. Does that make sense? All right? So, for instance, going back real quick, if we had something like A is to B is C is to D, if I alternate these two, the D and the A switch places. D over B equals C over A. I think actually you had to step out of the room for something when we were going over this. So, catching you back up just a little bit here from the other day. But it's just alternating, just switching places with two things. And again, in this case, instead of having a B, it's a 1 that we kind of envision being there. We envision the one that allows us to flip those. Make sense? All right, so coming back over here then, if we know that the mass is 212 grams, and if we know that the density is 2.70 grams per cubic centimeter, and make sure I'm not coming off the screen here. When I divide, first of all, I'm dividing 212 by 2.7 to get anyone? 78.51, blah, blah, blah. Now watch the units here. The grams and grams are going to cancel. But notice, the cubic centimeters is a denominator of a denominator. Do you see that? The denominator has its own denominator, and if something's a denominator of a denominator, remember we multiply by the reciprocal, it moves that unit back to a numerator here. Does that make sense? With a complex fraction. So rounding off to, how many sig figs, class? 3. We're going to cut it here and simply say our answer is 78.5 cubic centimeters. How many have that? For number 4. All right, good, Kendall. Questions on this? Does it make sense now? All right, and taking a look at number 6, small sample of pure uranium has a mass of 10 grams. What is its volume? Well, once again, if we're solving for volume, we're going to need this equation again. The V equals the M over the rho. Again, the only way we memorize it is this way. We don't want to memorize multiple equations. We'll memorize one way and be prepared to alternate if need be, or cross multiply if we're solving for the mass. Here we know the mass is the 0.10 grams. Density of uranium from that table, what is it?
18.7.
18.7. And again, that's grams per cubic centimeter. Again, the grams and grams cancel. Again, denominator of a denominator moves it up into the numerator. And the 0.1 divided by the 18.7 gives us 0.1 divided by 18.7, not the other way around. 0.1 divided by 18.7. 0.0053, keep going. 47, blah, blah, blah. How many sig figs in the answer? Either 2 or 3. I've got to go with the smaller number 2, so we'll cut it here and say 0.0053. There's my second sig fig here. The 4 doesn't quite bump it up. All right. How many had 0.0053 cubic centimeters on number 6? Questions on these? Do they make more sense now that we've gone over them? All right, Justine, so I want you to do problems 5 and 7. Take a moment to work problems 5 and 7, and let's see if we can take what we gained from the homework, gleaned from the homework, and progress just a little there. Do 5 and 7. A blast from the past here, number 5, right? Volume of a cylinder. We haven't seen that since 8th grade. All right. Pi r squared h. Now remember, you don't need to use 3.14 for pi. You can just use the pi button. Do we all know where the pi button is on the calculator? And we need help with that. All right, so what's the radius here that we're going to plug in? So we'll use pi. The radius here, class, is 1.8 centimeters. We're going to square that. Now notice that's centimeters that's being squared. So we're centimeters. And then the height is also another 3.2 centimeters. So that's 1, 2, 3 centimeters. Hence that's cubic centimeters. We follow the units here. All right, so pretty straightforward on the calculator. You'll do, I would start with the 1.8 squared order of operations. 1.8 squared. Let's try that again. 1.8 squared. There we go. Times 3.2 times pi equals, and what is the volume, that first number we had to find, class? 32.572, blah, 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 okay? Now, this may come in handy if we were to need to put it in the memory of the calculator. Kendall, this is something we've talked about in pre-cal. Are you familiar with memories on the calculator yet? All right, so you're using the same calculator I am, and your calculator has 3 memories. So tell you what, go ahead and get this number in the calculator again, 1.8 squared times 3.2 times pi. We're going to use memories quite a bit later on this year. We won't use them a whole lot here early on, but do want to make sure you're familiar with your calculator and able to use its features. All right, so you've got 3 memories, and the key is to store the number that's on the screen into the memory. This button here that says stow, that means store. All right, so you're going to stow it. Now you can either store it in memory 1 by hitting store 1, or store it in memory 2 by hitting store 2, or store it in memory 3 by hitting store 3. Which one do you want to store it in? Memory 1, right? So hit stow 1. And you'll see the number's still on your screen for you, but you see a little M1 that pops up there. Now go ahead and clear your screen off. In fact, you can even turn your calculator off. When you turn it back on again, it's going to be there. Even if the battery dies, I believe, the memory is still stored in there. So you could have your calculator off all summer, come back and like, oh, there's still something in the memory. I guess I forgot to clear it after the final exam. You know, so the value stays in there. To recall, that's what RCL means, is recall. So hit recall 1, and boom, there's the number for you. All right, so stow 1 puts it into the memory, recall 1 takes it out. All right, so we found the volume, and it says, what's its mass? So we're looking for the mass. We know the volume. This is how I'll notate things in this class. Is I'll say the volume is in memory 1. Michael, in your case, you may notate memory A, B, C, because you have lettered memories. We all have numbered memories. And there's one more number we need, and of course, class, that's the... We're finding the mass. We now know the volume. We also need to know the density. Good. So we went back and looked it up. It's cork. What is the density of cork? 0.24 grams per cubic centimeter. Now, what is the equation that I memorized that relates to these three variables, class? But I'm solving for the m. How do I solve for the m? How do I get it by itself, class? This time I'm going to multiply both sides by v. Because I'm not solving for a denominator. I just want to cancel the v, and there's my equation. M equals v times rho. So I've got the point, I've got this number. It's actually still on my screen, as it turns out. Maybe I didn't need the memory after all. I'm just going to multiply by 0.24. Or 0.24 times recall 1. And what do we get for the mass of this piece of cork, class?
7.81.
And notice we've got cubic centimeters and per cubic centimeters that cancel, leaving me with just grams. But how many sig figs am I allowed? 2. Every number they gave me was 2 sig figs. So I'm going to cut it off at 2 sig figs and say my answer is approximately 7.8 grams. How many had that answer? You had the 7.8 grams? Okay, questions on it now? Any questions on it now that we've worked it through? The next one's an interesting one. It says, what's the specific gravity of air? Well, what is air? What's in our air that we breathe, besides pollutants, which actually make up a very, very tiny percentage?
Oxygen.
Oxygen, right? That's what our lungs need. That's what our bodies need to breathe. What else? Nitrogen, that's what plants need to breathe. What else? You believe the global alarmist, tons and tons of CO2, which is actually great for plants. You know, anyway, does trap thermal energy more. CO2, a little water vapor in there. It's kind of a mixture. So if you go back, they actually should have air listed separately from these other substances, other gases. And the density of air, class, grams per cubic centimeter. And since air is obviously a gas, we're going to have to divide the density of the air by the density of the standard, which is, yeah, the hydrogen. So 0.000899, 4 zeros? Yeah, 4 zeros, 899. And what do we get for the specific? That can't be right. Try again. 0.00129 divided by 0.00. 0.00899. Calculator malfunction. All right, what do we get for the specific gravity of air, class? All right, these two numbers, how many sig figs in them? 3 and 3, so my answer will be 3 sig figs, and we'll just say it's 14.3, nothing, right? Specific gravity, no units. Questions on number 7? How many had that answer already? All right, good questions. All right, let's go ahead and next section in your notes to talk about what you read in your homework. So we'll give the math a bit of a break. Stop cheering. And talk about classification of matter. Next in your notes, classification of matter. A couple of things we want to get to first, and that is what all matter is composed of. At its most basic, all matter is composed of atoms. So if you'll get that term down, the atom is the most basic building block of all matter. Now, every year I get students in physics who are like, what is the most basic building block of all matter? Amino acids? Stop it, that's biology class. No, that's proteins. Proteins are atoms. Atoms are the most basic building block of all matter, because if you broke an atom down further, you would not have matter, you would have submatter, or subatomic particles. So the atom is the most basic building block of all matter, but atoms combine chemically together, and they form what are called molecules. Molecules are a chemical combination of two or more atoms. Molecules, chemical combination of two or more atoms. So the atom's the most basic building block of all matter. Molecules are made up of atoms that are now chemically combined. And understanding those two terms will help us to understand these two broad categories of matter. I don't know if you want to put together a flowchart type thing. Your book has a little bit of a breakdown here. I'm going to differ from the way they broke it down. I'm going to say all matter can be broken into two broad categories. The first of which are what we call pure substances. Pure substances. Substances that are the same throughout. That's what makes them pure, right? For instance, if you got a bag of pure sugar, no cockroaches, no sand, right? Just pure crystal sugar that's waiting to become diabetes one day. Pure substances. Okay, it doesn't become diabetes, it triggers it perhaps, okay? But pure substances. The first type of pure substance is what's called an element. And of course, you studied the table of the elements last year in chemistry extensively. An element is defined as a pure substance in which every atom is exactly the same. A pure substance in which every atom is exactly the same. And therefore, it cannot be broken into a simpler substance. An element is a pure substance in which every atom is exactly the same, and therefore it cannot be broken into a simpler substance. Basically, if you have pure anything on the periodic table, you have an element because it's a table of elements. For instance, pure oxygen. Right? You ever been to the hospital or maybe a nursing home and there's a sign outside warning no smoking, oxygen in use? All right, that tank, if it had pure oxygen in it, every single atom would be an oxygen atom. Now they're chemically combined, right? What is an oxygen molecule? Do you remember? O2, right? So there's two molecules or two atoms that combine to make a molecule, but even if you broke the molecule down, it's still oxygen. Every single atom is oxygen. Pure oxygen is an example of an element. If you had 24 karat gold, which is really, really weak, okay, that's why usually gold is reinforced with other things, but if you did, every single atom is a gold atom. It's absolutely pure of any other substance. It's not an alloy mixed with anything else. That would be an example of an element. Every single atom is exactly the same. You also have pure substances called compounds. A compound is a pure substance in which every molecule is exactly the same. A pure substance in which every molecule is exactly the same. For instance, pure water. Well, every molecule of water class is water chemical formula? H2O, yeah, you know this, yeah. H2O, right? Well, each atom isn't the same, right? There's two hydrogens and one oxygen, so it's not an element, right? You have a mixture of things. But if every single atom, or excuse me, if every single molecule is a water molecule, there's no dirt, there's no crystal of sugar or anything mixed in the water at all. It's just absolutely pure water. Everything is an H2O molecule. It's a compound. Right? The atoms themselves may differ, but the molecules are exactly the same. Pure table salt, right? Do you remember what table salt is? NaCl, sodium chloride, right? If every single molecule is an NaCl molecule, right? Then that absolutely pure, that would be an example of a compound. They're pure substances. Nice and clean, everything, there's a uniformity. So again, element class, every atom is the same. It can't be broken down anymore. Compound, every molecule is the same. And you could theoretically break those down further. Then we have things called mixtures. Like dog breeds. molecules, okay? You have multiple things all mixed together in there, okay? Mixture. Two types of mixtures. The first type of mixture is called a homogeneous mixture. A homogeneous mixture is a mixture that there's all different stuff in it, but everything is evenly distributed throughout the mixture. There's an even distribution of molecules. You don't find a whole bunch of this molecule over here and a whole bunch of that molecule over there, or different layers of molecules. It's just everything's evenly distributed throughout. For instance, when you make Kool-Aid, right? You're supposed to stir it and stir it and stir it and stir it until everything dissolves evenly, right? If there's stuff settled at the bottom, that's not a homogeneous mixture, right? You want everything to be evenly distributed throughout. By the way, you might have seen this word homogenized. Have you seen that word on a product before? What do you usually see that word homogenized on? Milk, right? It usually is pasteurized and homogenized. Pasteurized means they got all the junk, the bacteria out, right? Louis Pasteur, thank you. But homogenized means this: they mixed everything together, right? So for instance, you know this, when the milk comes out of the cow, right? There's the watery substance, and then there's the creamy substance. Y'all know what I'm talking about? Watery, creamy, okay? And the creamy is the globules, that's a great word, of fat, okay? And that's what gives the milk flavor. And then the watery stuff is the skim milk. Now, skim milk, they take and they scrape all the fat off the top, and literally it's just the watery substance, which is no good at all, right? It's not water, but it tastes like it pretty close. Okay. Anyway, well, what they'll do for different milk, like 1% milk, they'll take 1% of the fat, they'll put it back in. 2% milk, 2% of the fat. Whole milk gets 4% of the fat back in. I believe half and half isn't actually 50-50. I could be wrong with that. I want to say it's like 38%, something like that. But what they'll do is they'll put the fat back in. Well, naturally, the fat globules will rise to the surface. So what they do is they homogenize it. They put it through a chemical process where they make the globules evenly distribute throughout the milk, which makes all the milk white. So when you pour it in a glass, you see white milk. Now, have you ever opened a container of old milk? Have you ever looked at the top of it if you got past the smell long enough? And there's these globules floating at the top. It is unhomogenizing. The homogenization process doesn't last forever. So when the milk begins to spoil or go bad, it begins to unhomogenize, and you get clumps throughout the milk, okay? It has become now a heterogeneous mixture, which is what it naturally is anyway. A heterogeneous mixture. Heterogeneous mixtures are those mixtures that have some type of clumping, grouping, or layering of molecules. For instance, I think you might have seen this in chemistry last year where Miss Morse would have some chalk dust in her water. I don't know if she was cleaning her rags or if she put it there on purpose, but it never dissolves, does it? Sugar will dissolve into the water. Kool-Aid mix will dissolve into the water. Chalk doesn't. It just kind of stays floating there. I guess we'd call it a colloid if we could get it to stay suspended, right? But it's still a heterogeneous mixture because there's distinct places where there's more of this or that. My science teacher used the example of a salad. Heterogeneous mixture. You can see where the tomatoes are, the cheese, the carrots, it's all separate. But what if you took the salad, threw it in a blender, and ran it for a few minutes? You get this soupy substance. Now, it's still a mixture of all the stuff you used to see, but now it's all evenly distributed, and you drink it and call it juicing, and whatever, okay? And it's healthy. Anyway, but a heterogeneous mixture. There's some sort of clumping or layering. This would be, again, milk before it gets homogenized, where there's this layering effect there. Questions on pure substances and mixtures. You should have learned all this last year in chemistry, is that correct? All of this as I'm teaching you, like, oh yeah, I remember that. Be sure to tell Miss Morse she'll like you better. All right, anyway, questions on the types of substances. All right, also want to talk about states of matter, next thing in your notes, states of matter. And this should be a review even from your elementary days, I believe. You've known this stuff for a while, so we'll move quickly through this. States of matter. There are three main states of matter, class. Solid, liquid, gas. But there is a fourth state of matter that's kind of cutting edge now, called plasma. We'll look at that in a minute. But let's get the big three down first. Solids. Solid has definite shape, definite volume. Solids, definite shape, definite volume. This calculator has a definite shape to it, right? And a definite volume. It's not randomly expanding or randomly contracting. That would be a little strange. It's also not sort of wiggly. right? Where it changes its shape as, okay, water does. I'm not doing anything to the water, but water just easily changes shape, right? The solid doesn't. Now, can I change the shape of the calculator? If I apply force to it, yes, I can change the shape. I'm not going to. But I could, but other than, unless some force is acted on it, definite shape. For instance, people bring up, what about Play-Doh? Is it a solid, or is it a liquid, or is it a semi-solid? Well, if you don't touch the Play-Doh, does it change its shape? No. If you set a blob of Play-Doh on the table, it'll sit there, okay? It's a solid, okay? If you try to just put a blob of water, obviously that'll spread out. So water's liquid. Liquid has a definite volume, okay? It doesn't expand or contract on its own naturally, though there's a little expansion, contraction as temperature changes. We'll look at that later, but pretty much definite volume, but no definite shape. A liquid takes the shape of the container. So liquid, definite volume, but no definite shape. And of course, gases, no definite volume and no definite shape. Gas can be whatever shape, and it can fill the room, right? On a positive note, you could spray a little air freshener or put a little lavender hand sanitizer on, and the fragrance just fills an entire room. It was contained in this little bitty can, just a little spray, and all of a sudden the entire room smells good. There are also negative examples. We won't talk about those. And then the last state of matter is plasma. Now, plasma is believed to be the most abundant state of matter in our universe because it is believed that plasma is what the stars are made of. Plasma, if you'll get this down, is a highly ionized gas. Plasma is a highly ionized gas that only exists at extremely high temperatures. Based on that definition, again, we believe the stars to be plasma, and if that's so, most of the universe is emptiness, right? But within that emptiness, which is non-matter, we have massive balls of what we believe to be plasma, which would then make plasma more abundant than any other state of matter. How does plasma exist? Very quickly. You remember talking about halogens last year? On the periodic table, it's column 7, right? Which means 7 electrons in the outer shell. Which means halogens, as a general rule, pull 1 electron in and bond that way. Halogens don't give up electrons easily. Noble gases won't bond with anything. That's why they're noble, they're stuck up, right? They're noble gases, they can't bond with anything because they've already got the octet satisfied, right? They definitely don't give up electrons. But at extremely high temperatures, you could strip an electron from either a noble gas or a halogen. And if you do, it ionizes the gas. That's plasma. Does that make sense? So how do you ionize the gas? Well, it's high temperature ionization of either your halogens or your noble gases, and that also causes that glowing that we see as well. So that's what we believe plasma to be. No one's ever actually been to a star to visit. The Polish were going to send a team of astronauts, and they were going to send them at night, so that way they would be safe to go to the sun, but we never heard back. I was kind of kidding, that's a joke. Anyway, all right, no homework this evening. Have a wonderful rest of your day, and you are dismissed.